Okay, just like in the previous problem, we were given the limit, and we want to prove that the limit is L. But usually to find this limit, we just do direct substitution, and this particular one plugging 0 directly in, and the cube root of 0 is just 0. But now we want to prove that the limit is 0. And we're going to use our definition up here. And the idea here is we want to find a delta. Okay, we want to find a delta. All right. So I go ahead and plug in our stuff into our statement here. That stuff happens to be, this remember is C, so this is going in here, and this is our f of x minus our L. And what we do here is we work backwards. I'm going to take this, okay, and solve for x, or find the solution set. Now I drop the absolute value signs, and we have 3 roots of x is less than epsilon. Now we would normally also, when we drop the absolute value signs, we would flip this sign and make this negative. However, I'm just doing everything above 0. Let's look at a graph. Okay, so we're just looking at this interval here above 0. You know, you could put this in right here. This would be epsilon, negative epsilon cubed. But anyway, so to find the solution here, we cube both sides. Right, it gets rid of this cube root, and so then we're left with x is less than epsilon cubed. Okay, so this is our delta. Our delta is going to end up being this difference right here, this distance, okay, which happens to be epsilon cubed. So that's all you have to do really to find the your delta, right? So we work backwards, and this is what our delta happens to be right there, and we can stop. So there it is. Alright, in this one here we've got the limit of x squared as x approaches 0 is equal to 0. So we do the direct substitution. I plug 0 in, and 0 squared is 0. Now, just like the previous problem, right, we're given the definition of the limit up here, and we want to show that our limit is actually equal to 0. But to do that, all we really need to do here is just construct a delta. We just want to construct a delta. So once again, we're working backwards here. So we're given this, drop the absolute value signs, right? You'd be bringing the 0 over, but epsilon plus 0 is just epsilon, and then square root both sides. So we end up with x is less than the square root of epsilon. So we can let our delta equal the square root of epsilon. Even though I found x is less than epsilon, remember that we're coming over in this direction, a negative square root of epsilon. So keep that in mind. Okay. Anyway, so our delta is the square root of epsilon. Now remember, back when we talked about the first thing we talked about in the discussion on the definition of the limit, that we have to choose a delta so that every x value that we choose as we get closer and closer to 0 must be within that interval. F of x minus the absolute value of f of x minus L has to be less than epsilon. Okay, and we talked about that. So this guarantees us that that this interval right here is going to guarantee us that that we're going to be within that that absolute value of f of x minus L is less than epsilon.